Today we'll be talking about the torsional spring powered vehicle project. In our group, we have Anila Ramratan, myself, Orlando Radix, Nukosi John, Ahmad Lachan, and Nita McKenzie. And our lecturer is Iran Amrali.
My name is Nkosi and I will be speaking on the problem definition. Our team was charged with developing a mathematical model for predicting the distance traveled by the vehicle after a torsional spring was moved by an angle between 30 and 330 degrees. This program will simulate on Excel the changes in a vehicle distance caused by these various masses, which is taken from percentages of 20 to 40% of the vehicle's total weight. In order to create a prototype that will accurately reflect this values, our group will apply this mathematical model. In the end, our group would take into account any deviations between the theoretical values and the experimental values of the project. And I'll pass you on to Orlando, who will speak on the mathematical model.
So here we have the mathematical model. We have G as the mass, we have T as the torque, and K as the spring constant. And this is the equations we came up with. GQ double dot plus KQ, which is the spring, and equals to theta. As we came up with the transfer function, this is how we derive the transfer function by taking Laplace of the equation. We assume that all initial conditions is equal to 0, and we came up with the transfer function where we know QS over TS is equals to 1 over GS squared plus K. We substitute the values and we substitute the values for K and the values for J mass, and we came up with the equations. The response systems of the unit step, was 1 over S. And how we came up with that, we take Laplace transform, we take Laplace partial fractions. And we went from S to to the T domain, where we say QT is equal to 0.714 minus 0.65 over the sine T. Here we have the 20% of the 0.6, which was the mass of the vehicle. We have the 25% of the 0.6. We came up with that calculations as well. We have the 30% of the 0.6. We did the calculations as well with that. We came up with the answer. We have 35%, and we have the 40% of the 0.6 mass of the vehicle. After we get the values, we had the theoretical mass, the mass of the vehicle. We had the actual distance or the experimental distance the vehicle traveled. The theoretical distance is the calculations we came up with while we was calculating, and we have the time. And this is the graph showing how the distance time graph, how the system behave or responds. We have the 60 degrees angle. So what we did, we had from 30 degrees, we had 60 degrees, and we had from 180 degrees. Each had a different graph and a different response time. I'll hand you over to the next speaker now. So now we will be going over to the demonstrated video of the prototype. So basically, this is the vehicle. When you crank this up, so you basically have the spring at an angle.
Good day, sir. My name is Ahmad Lachan. So, the theoretical values, right? This is derived from the mathematical equation and formulas that take into account various factors such as speed, time, acceleration, and resistance, etc. There are ideal conditions, such as perfectly flat roads, constant speed, no wind resistance, and no mechanical inefficiencies. And also in theoretical, you assume there are assumptions such as neglecting air resistance, etc. You also predict or estimate the distance the car should travel under specific conditions. Now, in the experimental values, real-world measurements are used to obtain the actual values by driving the car itself. Environmental factors contribute to this, such if you take into account world factors such as road conditions, wind resistance, tire conditions, and the car's mechanical efficiency. As you can see from the table, the actual distance compared to the theoretical distance is slightly off. And this is because of the experimental factor, where such as the tire was wobbling in the previous video, as you can see in the demonstration, the tire was wobbling, so which made the car to actual slow up in speed, which causes to travel in a lesser distance. And this is why the calculation is slightly off. And another thing is the tile. The tile is a smooth surface where there is no grip. So this also contributes to the lessening of the speed.
Okay, so my name is again, and I'm talking about the dimensions and the sketching of the prototype of the vehicle. So we have the body, which is made out of polycarbonate, or as we locally call it, hard plastic. I now go on to the dimensions of the body. So we have the length and the width. The length of the body is 202.2 millimeters, and the width of the body is 50.8 millimeters, and the height is 76.2 millimeters. And there we have a front view of how the body is made up. Here you can see it is hollow on the inside. The tire, the diameter, or the radius of the tires, however, is 152.4 millimeters, and that's for the back tire, and the front tire is 101 millimeters as its radius for the front tire. We also have the spring, which is 60.082 millimeters long, and it has a constant of 1.3 Newton meters. As you can see here, we also have wood as a part of the prototype and a steel rod.